So what are we gonna do today? I did make a mistake with the recording last time and the quality, and it just was directly something to trash. So I'm trying to do it again, but basically that's kind of lost. So the commentary on all the derivative functions and whatnot is kind of lost. So because essentially what I was trying to do is I was trying to understand and to basically fix. So what I was trying to do, I was trying to look at the backward pass is one thing. So we took a look at the changes in here, and we could see that no changes were being calculated. So something is kind of going wrong. And if I am looking at the train file, this is where I have all the loss function stuff, right? Which kind of seems wrong. So what I did is I asked Ghostwriter to kind of give me, I just re-described the situation a bit more, and kind of it gave me that categorical cross entropy loss, which kind of makes a bit more sense, because I was thinking the two things that don't make sense to me at the moment. One thing is, well, we used to have this loss function that just takes a look at it just takes a log of the predicted distribution or the predicted category, right? But it does not look at every other probability that is predicted, right? And so essentially, if I look at not test, if I have train and then I have the actual neural network here, and then in the back, the other stuff that's not working well is the backward stuff, this thing here. Right, so here we're just kind of minusing the probabilities, the predicted probabilities, and minusing the actual probabilities. Which, what I try to basically describe here is like that you get something like that, right? So you get like if this is your true distribution, and again, some of these things might be 0.5, you know what I mean? Like this might be 0.5, and maybe this is 0.5 as well, but then it's kind of like 0 on that end, right? Just to align it well. You know what I mean? We really, I think it would make more sense that we take a look at that our loss is sort of a measure of the difference of every single probability, right? Unless, yeah, maybe, I don't know, maybe not, right? Maybe you want, I guess my feeling is, my assumption is it should give us a more nuanced sort of version, right? Of a comparison. So because it takes into account all the other stuff, even though we're only going to take the highest probability. But then still, like, that's cool. But then I don't think we should be taking these. Why aren't we actually taking? Why aren't we actually taking these directly, like this output, right? Kind of the element-wise comparison. Because, and that's kind of, yeah, and that's what I finished the other video, that basically it was, the recording was to trash. And that brings me to this drawing here, I guess, that I try to do. Sorry, it's awful. Because what I was trying to basically draw here is that, and I ended up, sadly, having to Google SGD, but maybe. So can you explain in detail how SGD works? We don't want to explain code. We want default. See, because essentially what SGT is doing is calculating the derivative, right? And then is using that derivative, that gradient, to update the stuff. Because essentially the idea is, I don't know, I cannot move this here now. I need to go full screen. But the idea here is, if your function is like that, going up, your derivative is like plus 6, right? So it's like, let's say, right? So like that's the one that you're looking at, not the one that goes down. This means that, and that's kind of the function itself, right? It's just a constant function of 6. Because essentially, it will give you in higher dimensions like an array, right? Because this has magnitude and direction. The sign gives you direction. It's telling you whether you should add or subtract. In this case, it's plus because it means if you increase this element here, you're gonna get a higher output. That's what we want to know. Obviously, if we have 2 dimensions, that's just going to be like the direction of that array as like interpreted as a vector, or multidimensional vector, right? But that's kind of what this is saying, right? Now that obviously doesn't have to be, the derivative doesn't have to be a constant. It can be a more complicated function, which then I don't know how you actually implement that because it's got a variable that you need to replace, I guess, at some point. But it's this derivative that you wanna basically use. Now, the derivative, the reason why I believe this is what's happening is that I believe that in a simplification, as a simplification, it just works, right? Because obviously the derivative, you want this to be something that is easy to compute, that you don't spend a lot of resources on it, because it's happening all the time. So for the first for the outermost layer, right? What you want to do, so this dw2, is you want to take that derivative and use it to modify whatever, right? Now, in the case that we're having here, we're having 2 probability distributions. How does this make sense at all? Because and this is where it's getting hard to visualize, right? Because it's matrices, and maybe I should be doing sort of a very small example. But essentially, you know, we've got, maybe we need to understand these. Maybe you need to understand what are these components better. Logit, so we have the softmax function in here to get the probabilities, but again, maybe this should happen with the logits, right? But then this will make some sense because y is not in logit, it's in y is an actual true. Yeah, but y is a true probability. So y is, yeah, that's the messed up. I mean, of course, this should probably be logits, and I already tested it in last video. That logits actually gives you a much more accurate. It gives you a better. It just works better. And essentially, give me a second. Baby's crying. Let's pause the recording. Okay, I guess we're back. Yeah. So, logits probably is better. True. This is just to kind of turn it into probabilities, but that's kind of probably better to do. But anyway, even, right? Like even. Logics will not tell you. My point is, if we look at this example, we're talking about like, we know it's easy to think about because the x dimension are integers, right? So, and that's not an alpha, it's an x. So that clearly is something that tells you just increment that x, right? And then you'll get a higher y. What I think what we have to dig into, and maybe I'll just break this video into two just to make sure that now the recording is not spoiled before I dive into more interesting stuff. But what we need to do is we need to understand the input for these, like this derivative, this function that we're trying to do derivative of, it's encoded in here, right? So that is actually what this code that Ghostwriter gave me is trying to do here with these reshapes and these dots and the dot product here and the sum here. This is what I don't understand, right? Because essentially, this is what dictates the change that needs to happen. So maybe the first thing that I should be doing is try to understand, first of all, what the architecture of my network is, because that dictates how I'm going to be using this. Because yeah, essentially, and what can I can calculate the derivative of these, but this derivative, like I don't like, to me this has nothing to do with the input. There's no, like, it's just a fucking subtraction. So, you know, I'm subtracting something from something else. This is not like, it's not something that is a function of the input, right? It's not something that is that is a function of the input anyhow. Oh, what does this say? So this says that now let's talk about gradient descent more in general. Give me an outline of the idea instead. Compute the output, pass the input data through the model, and compute the output predictions. Calculate the loss, compare the predicted output with the actual output, and calculate the loss. The loss function quantifies how well the model is performing. Compute the gradient. Calculate the gradient of the loss function with respect to each parameter. The gradient represents the direction and magnitude of the steepest ascent of the loss function. And update the parameters, exactly. But that is kind of what's not clear to me here, right? Essentially, what we're gonna have is, what do we have? What is the forward pass calculating? First is doing a dot product between the input and this W1, plus adding it some kind of bias. And then it's doing this for some reason, calculating some A1. So what is the purpose of these? I think I asked already, but like, subtopic, what's the line? And you know, what is it doing? So it calculates the activation values for the first hidden layer of the neural network. Oh, so this is activation. Okay. It's a hyperbolic tangent of Z 1. That's the first layer. Is the weighted sum of all the inputs for the first hidden layer. The result represents the activation values for the first hidden layer, which are then used in subsequent calculations of the network. Well, then you take there's a hyperbolic tangent though. So and then we're using these with W2 and B2, so that's like another like the Z2 is the actual logits. Essentially, W2 is just a hidden size by output size matrix. Hidden size by output size matrix. And we're basically taking these whatever activation values, multiplying them. Maybe this is the Y activation. Why can't we use Z1 directly? Why can't we use Z1 directly instead of having this extra A1? So Z1 represents the input to the activation function in the network. The output of the activation function is used to and the backward transfer. The purpose of applying the activation is to introduce nonlinearity into the network. Okay. And allow it to learn more complex patterns in the data. This directly without applying the activation function would result in a total, like a complete linear transformation, which limits. Okay, so it's simply like kind of like basically adding more complexity to the mix. Shell. So so that's a hyperbolic tangent function. Okay. Zero stays untouched. Yeah, but that's kind of in a way normalizing the whole thing. Why is this even a good function? It is not the activation function. Non-activation functions are crucial. That was the model to learn complex relationships. Simply be a linear model. Zero-centered. The sample values range from -1 to 1. This property makes it easier for the network to converge during training, especially when using weight initialization techniques that assume zero-centered. Okay, interesting differentiability. Is differentiable everywhere, which is important for the training. Okay, fair enough. So this is just something to introduce some, non-linearity. Okay, but was it non-linear? So that mean for a function. No. Isn't it like it's not about being continuous, right? So the additive and scaling property. A linear function, it satisfies additive and scalability. Yeah, exactly. Okay, so can you uh so is it that it doesn't fulfill this stuff, I guess, or this stuff? Can you plot tan h x tan h y? Let's see. See what happens. So where's the shell? Shell. I thought I was running it. Uh, why isn't the output loading? Wow. Uh-huh. So yeah. So this means it's like, how do I have to modify each weight? You know what? We should really do a very, very small example of this, like a toy example with like a 2x2 matrix or something like this. So it will be kind of meaningful still. Python test.py. Okay. What the hell? Uh, Zoom. How do I see? That's the wrong test. That's the wrong test. What I want is one to plot x plus y. Wait. What am I doing? Plot. Let's do like this. Okay, so I don't care about the first one. Plot these things exactly and see if the second and the third one. Oh, doesn't matter. The first and the second are the same because if they're not linear, yeah, they should be the same. These are with the multiplication constant thing, right? And I'll have to leave it here, folks. Why isn't it showing? Yeah, so now let's go maximize. And they're different. They're different. Yeah, they're different. So this is a not linear function. Awesome. Okay, cool. But at least we've proven that in a very analytical way, or visual way. But yeah, okay. So, but we have, I think I have a better understanding of this. But it's still, okay. So still, I need to basically, to me, it's still not clear that doing this subtraction is equivalent to doing the derivative. Well, it tells you in a way which components, like, it tells you in a way that here you shouldn't do anything. It tells you in a way that you predicted this to be false, and now it should be true. So it's like there's a -1. Obviously, you probably have to minus these, right? Or maybe do predicted minus true, right? That's probably better. Isn't predicted minus true better? And yeah, maybe that is an indication that but it's still the outcome. That's not what I want. That's not what I want. I want an expression. I want something that tells me something that is related to the input. That is not related to the input at all. That's what bothers me anyway. Hopefully this video didn't go that bad from a quality perspective.